A dead star spins in the dark, ticking with a rhythm more precise than any clock on Earth. This is a pulsar, and the universe has built around it the most exacting laboratory we have ever found. Our guide through this cosmic experiment is a pair of these stellar corpses, locked in a frantic dance known as the Hulse-Taylor binary pulsar. By the end of our journey, you will understand how this distant duo gave us the first proof that space itself can ripple with gravitational waves. For decades, it has tested Einstein's theory of gravity under conditions of unimaginable force, acting as a natural referee in a contest of cosmic laws. What hidden clues are written in the steady decay of its orbit, and how did two astronomers decode a message sent by colliding stars? The answers redefine our grasp of reality itself. What does it mean to find a perfect clock ticking at the heart of chaos? To build that perfect cosmic laboratory, nature first needed to forge the perfect clock. This is the story of a pulsar. Think of a star many times more massive than our sun, a giant that has lived its life and now faces a violent end. In its final moments, it does not fade quietly. It explodes in a supernova, an event so powerful it outshines entire galaxies. What remains is not a ball of fire, but something far stranger and denser. The star's core collapses under its own gravity, crushing atoms into a sphere of pure neutrons just a dozen miles across. A single teaspoon of this material would weigh as much as a mountain. This is a neutron star, and when it spins, it becomes something we can hear. A neutron star is born spinning furiously, and it possesses a magnetic field trillions of times stronger than Earth. This combination creates a celestial lighthouse. From the star's magnetic poles, intense beams of radio waves and sometimes other radiation blast out into space. Because the magnetic poles are often misaligned with the star's rotation axis, these beams sweep around like the beacon of a lighthouse. If Earth lies in the path of that sweeping beam, we see a flash, a pulse of energy with every single rotation. That rhythmic flash is a pulsar. It is not the star itself pulsing, but our line of sight cutting across that relentless spinning beam. The data from our radio telescopes translates this into the iconic sound, a metronomic beep, beep, beep echoing across the light years. This is where the magic for physics happens. The spin of a neutron star, especially a young one, is incredibly stable. The pulses arrive with a regularity that rivals, and in many cases surpasses, the most precise atomic clocks humanity has ever built. We are talking about a spinning ball of ultra-dense matter, heavier than our sun, keeping time with a precision of 1 part in a quadrillion. It is a natural metronome set by the laws of physics themselves, ticking in the void with unwavering discipline. This precision transforms the pulsar from a cosmic curiosity into the ultimate tool. It becomes a clock we can use to measure the fabric of space-time around it. Any tiny change in the rhythm of those pulses is not a flaw in the clock, it is a clue. It is the universe whispering about distortions in gravity, about the presence of a hidden companion, about the very curvature of space itself. The stage was now set, but the universe had an even more astonishing experiment in mind. But a clock alone can only tell the time. For a real experiment, you need a disturbance, a force acting upon it. In 1974, two young astronomers, Russell Hulse and Joseph-Taylor, were conducting a systematic survey of the sky with the massive Arecibo radio telescope in Puerto Rico. Their goal was to find new pulsars to map these cosmic lighthouses. One day, their data revealed a signal that was different. It was a pulsar ticking with that incredible regularity, but its rhythm was doing something strange. The time between pulses was not perfectly constant. It was speeding up and slowing down in a smooth, repeating pattern. For Hulse and Taylor, this was not an error in their equipment. It was a signature. That regular variation in the pulse timing was the telltale sign of a Doppler shift. the same effect that changes the pitch of a siren as an ambulance races past you. The pulsar was moving, being pulled first toward us, making the pulses arrive a little faster, and then away from us, making them arrive a little slower. This could mean only one thing: the pulsar was not alone. It was locked in a gravitational dance with another massive object orbiting around a common center of gravity. They had discovered the first known binary pulsar, designated PSRB 1913+16. This was the eureka moment. They had not just found a new celestial object, they had stumbled upon a ready-made physics laboratory of unparalleled precision. Here was a super-dense, perfectly ticking clock in a wildly accelerating orbit. Every aspect of its motion could be tracked by the slight changes in its rhythmic beep. The discovery itself was a monumental achievement, a testament to meticulous observation. But the true revelation was what this dancing pair would reveal over the coming decades. For their work in opening this new window onto gravity, Russell Hulse and Joseph-Taylor were awarded the Nobel Prize in Physics in 1993. The universe had provided the experiment, and now it was time to read the results. This cosmic duet is a spectacle of raw power and precision. Picture two city-sized spheres, each containing more mass than our entire sun, separated by a distance roughly equal from the Earth to our moon. They do not drift lazily like planets in our solar system. They whip around each other at staggering speeds, completing a full orbit in just under 8 hours. Their dance is not a perfect circle, but a stretched, elliptical path. This high eccentricity means their separation varies dramatically, from a close, frantic embrace to a wider, slower arc. At their closest approach, the gravitational forces are almost beyond comprehension, warping the space around them into profound curves. This is not the gentle tug of gravity we experience on Earth. In our solar system, Newton's laws describe planetary motions with incredible accuracy. But here, in this ultra-dense, ultra-fast, ultra-strong system, Newtonian physics begins to stutter. The rules change. The predictions of Einstein's general relativity, which treats gravity as the curvature of space-time itself, are no longer tiny corrections, they are the main event. The Hulse-Taylor pulsar exists in a realm where space and time are not a static stage, but a dynamic, malleable fabric being stretched and squeezed by these incredible masses. Every single pulse from that lighthouse clock carries a record of this distorted landscape, a direct signal from the warped geometry of the universe. Einstein's theory of general relativity came with a radical set of predictions for a system exactly like this one. It was as if he had left a detailed playbook for the behavior of gravity under extreme conditions, a list of cosmic homework assignments that no laboratory on Earth could ever hope to complete. For nearly 60 years, these predictions were elegant mathematics waiting for a real-world test. The Hulse-Taylor binary pulsar was the first natural experiment powerful enough to check his work. The theory forecast several subtle but crucial effects that Newton's simpler model of gravity simply did not include. First, there is the periastron advance. Think of the elliptical orbit not as a static loop, but as a slowly rotating rosette. The point where the two stars are closest, called periastron, gradually shifts around with each orbit. Mercury does this in our own solar system, a tiny effect that puzzled astronomers for centuries until Einstein explained it. For the binary pulsar, this rotation is not tiny, it is enormous, swinging around by about 4 degrees per year. That is over 35,000 times faster than Mercury's orbit processes. Second, there is gravitational time dilation, often called the gravitational redshift. The intense gravity of the companion star acts like a well, slowing time itself for the pulsar as it swings closer. This makes its clock pulses appear to slow down from our distant vantage point, then speed up again as it moves away, an effect baked right into the timing of those radio beats. Third, there is the Shapiro delay. When the pulsar signal passes very close to its massive companion on its way to us, the curved space-time around that star forces the light to travel a slightly longer path. It is like running on sand instead of pavement, adding a minuscule delay to the arrival time of each pulse. But the most profound prediction of all was gravitational radiation. Einstein's equations showed that accelerating massive objects like these two stars whipping around each other should not just bend space, they should send ripples through it. These ripples are gravitational waves, and they carry energy away from the system. That loss of energy has a direct, observable consequence. The orbital dance should slowly decay. The two stars should spiral inward toward each other, imperceptibly at first, but measurably over time. This was the grandest, most elusive prediction of them all. For the first time, we had a laboratory where we could look for all these effects simultaneously, using the pulsar's impeccable rhythm as our probe. The universe had provided the test, and now the ticking began. The rhythm of those pulses held the answer to Einstein's boldest prediction. For decades, astronomers pointed their telescopes at that distant point of light, listening to its metronomic beat. Each beep was a timestamp, a data point in the longest-running and most precise experiment in astrophysics. Their goal was to detect a specific, subtle change in the music of this cosmic dance. According to general relativity, the furious orbital motion of these two massive stars should not be silent. They should generate ripples in the fabric of space-time itself, gravitational waves that carry energy directly away from the system. Think of it like two children spinning in a pool, their motion sending out waves across the water. Those waves take energy from the children, and they gradually slow down. For the binary pulsar, this energy loss has a direct consequence. The orbit must decay. The two stars should spiral inward toward each other ever so slightly with each passing year. But how do you measure the imperceptible tightening of an orbit light years away? You use the pulsar's own heartbeat as your ruler. As the orbit shrinks, the stars complete their frantic loops just a tiny bit faster. This minuscule change in orbital speed translates into an equally tiny but cumulative shift in the timing of the pulsar's radio pulses. It is an effect so small it would be lost in the noise of any less perfect clock. Over a single orbit, the shift is negligible. Over a year, it becomes measurable. Over decades, it paints a picture of stunning clarity. The teams, led by Hulse-Taylor and others, tracked these pulses with relentless patience. They accounted for every possible contaminant, the motion of the Earth around the Sun, the drift of our solar system through the galaxy, even the slight delay as the signals passed through the thin gas of interstellar space. What remained was the pure signal of orbital decay. When they plotted the data, the result was a graph of breathtaking agreement. It showed the observed shift in the time of closest approach, the periastron, accumulating year after year. After 30 years of observation, the line on that graph matched the prediction of Einstein's equations with a precision of better than 0.2%. The two stars were spiraling inward exactly as fast as general relativity said they should, losing energy to gravitational waves. This was not just a confirmation of a theory, it was the first indirect proof that space itself could ripple. The universe had been conducting the experiment all along, and we had finally learned how to read the results. That orbital decay was the headline result, the splashy confirmation of gravitational waves. But the true strength of this cosmic laboratory lies in its ability to run multiple tests at once, cross-checking Einstein's theory from every angle. While the stars were slowly spiraling inward, their elliptical path was also performing a second, equally precise dance. The orbit itself was slowly rotating. This is the phenomenon of periastron advance. Picture that stretched oval path the two neutron stars trace around each other. Now imagine that entire oval is not fixed in space. It slowly swivels like a hula hoop being gently twisted. the point where the stars are closest, the periastron, steadily marches forward around the center of mass with each completed loop. It is not a perfect ellipse that repeats, it is a rosette pattern, a cosmic spirograph drawn by gravity itself. We see a miniature version of this in our own solar system with the planet Mercury. Mercury's orbit also processes its point of closest approach to the Sun, shifting very slightly over time. For centuries, most of that shift was explained by the gravitational tug of the other planets, a Newtonian effect. But a tiny leftover portion, just 43 arcseconds per century, stubbornly refused to be explained by Newton's laws. That tiny discrepancy became one of the first great triumphs of general relativity. Einstein showed that the Sun's mass curves the space-time around it, and this curvature adds an extra twist to Mercury's orbit, accounting for the precise amount of that leftover drift. Now take that subtle, hard-to-detect effect and amplify it beyond belief. In the Hulse-Taylor system, there are no other planets to complicate the picture. The advance is driven almost entirely by the fierce curvature of space-time generated by the two neutron stars themselves, and it is not subtle. The orbit processes not by tiny arcseconds per century, but by a staggering 4.2 degrees every single year. To grasp that scale, the binary pulsar's orbit completes a full 360-degree rotation in about 85 years. Mercury would take over 3 million years to do the same. This is Mercury's advance on cosmic steroids, a relativistic effect so magnified it shouts from the data. Measuring this required the same exquisite timing of the pulsar's clock. Astronomers mapped the precise arrival time of pulses throughout the 8-hour orbit. As the pulsar swung through the closer, faster part of its ellipse and then the farther, slower arc, the ticking pattern created a detailed velocity map of its motion. From this map, they could chart the exact shape and orientation of the orbit. Year after year, they watched that orientation relentlessly turn. The result was another bullseye for Einstein. The observed 4.2 degrees per year matched the prediction of general relativity to within a fraction of a percent. Here was a second, independent line of evidence, carved into the rhythm of the pulses, confirming that the fabric of space-time around these massive objects is not static, but a dynamic whirlpool that drags the very path of the stars along with it. But the tests did not stop with the orbit's shape or its slow decay. The pulsar's own heartbeat, its steady tick, carried an even more intimate secret about the nature of reality. As it raced along its elliptical path, the pulsar was not just moving through space, it was moving through time in a profoundly uneven way. Two separate, powerful effects were at work on its internal clock. The first comes from its sheer speed. According to Einstein's special relativity, time slows down for any object in motion relative to an observer. The faster you go, the more pronounced this time dilation becomes. For the pulsar, this means that as it whips around the closer, faster part of its orbit, its internal processes, including the mechanism generating its radio pulses, run slightly slower from our perspective. As it moves to the slower, wider part of the ellipse, this effect diminishes. The second, and even more mind-bending effect comes from gravity itself. General relativity tells us that gravity is not just a force, it is the curvature of space-time. A massive object like the pulsar's companion star creates a deep well in this fabric. The closer the pulsar swings to its companion, the deeper into this gravitational well it travels, and the stronger the pull on time itself. In a strong gravitational field, clocks tick more slowly. This is gravitational time dilation, often called the gravitational redshift. So, at its closest approach, the pulsar is both moving fastest and feeling the strongest gravity. Both effects conspire to slow its clock down the most from our distant vantage point. When it is farthest away, moving slowest in a weaker gravitational field, its clock runs closer to our normal rate. The result is a complex, rhythmic modulation in the arrival rate of the pulses, a symphony of time distortion composed by the laws of relativity. For astronomers, the challenge was to untangle this signal. They had to separate the slowing of the clock due to motion from the slowing due to gravity. It was like listening to a song with two overlapping rhythms and identifying each individual beat. By mapping the precise timing of pulses against the known position in the orbit, they could mathematically isolate the contribution from gravitational time dilation. The data revealed a clear, repeating pattern that matched Einstein's combined predictions with extraordinary precision. This was not just a test of an equation, it was direct evidence that time itself is not absolute. It is a local experience stretched and compressed by speed and gravity. The universe was using the pulsar's unwavering rhythm to demonstrate with crystal clarity that the flow of time depends on where you are and how you are moving. A second passing on that distant neutron star is not the same duration as a second here on Earth. While time itself was stretching, the very path of light was bending on its journey to us. This final, exquisite test is known as the Shapiro delay, named for the physicist who first predicted it. Picture the binary system from our distant vantage point on Earth. As the two stars whirl in their tight orbits, there are moments when, from our line of sight, the pulsar passes directly behind its massive companion. When this happens, the beam of radio pulses we rely on must travel through the severely curved space-time surrounding that dense neutron star to reach our telescopes. According to general relativity, light always follows the shortest path through the curved geometry of space-time. But near a massive object, that shortest path is longer than a straight line through flat space would be. It is as if the light must trek through a deep, invisible valley created by the companion's gravity, rather than skipping over a flat plane. Think of two hikers traveling between the same 2 points. One takes a direct route over a gentle hill, arriving quickly. The other is forced to descend into a deep ravine and climb back out, adding significant time to their journey. The radio waves from the pulsar experience a similar delay when they graze the companion's gravitational well. This delay is incredibly subtle, adding only about 100 microseconds to the travel time of the signal, a fraction of a blink. But for a clock as perfect as a pulsar, that delay is not only detectable, it is a precise measurement. Astronomers looked for this signature by carefully tracking the arrival times of pulses throughout the entire orbit. They predicted exactly when the Shapiro delay should be at its maximum, when the pulsar was most directly aligned behind its companion. The data revealed a slight, recurring lag in the pulses at those precise orbital phases, a lag that matched Einstein's predictions with remarkable accuracy. This was more than just another checkmark for relativity. The Shapiro delay provided crucial, independent information that other measurements could not. The exact shape and magnitude of the delay curve told scientists two vital things: the tilt of the orbital plane relative to our line of sight, and most importantly, the individual masses of the two neutron stars. By combining this data with the measurements of orbital decay and periastron advance, they could solve for these masses with unprecedented precision. They determined the pulsar itself weighs about 1.4 times the mass of our Sun, and its silent companion is very similar at about 1.39 solar masses. This agreement, where multiple independent relativistic effects all point to the same consistent numbers, is what makes the Hulse-Taylor system such a powerful proof. It is not one experiment, but a suite of them, all running simultaneously in nature's own lab, all confirming that gravity is indeed the geometry of a dynamic, malleable universe. The ultimate power of this cosmic laboratory was its ability to solve for the unknown. Each precise measurement of the orbit's decay, its rotation, and the delays in the signals gave astronomers not just confirmation of a theory, but a set of interlocking equations. They could plug the observed numbers into the framework of general relativity and solve for the fundamental properties of the system itself. This was the hidden prize, a way to weigh the invisible. Determining the mass of a distant star is notoriously difficult. For a solitary object, it often requires guesswork based on models of stellar evolution. But for this binary pair, the extreme physics provided the perfect scale. The rate of the orbital decay depended on the masses. The amount of periastron advance depended on the masses. The precise shape of the Shapiro delay curve depended on the masses and the orbital inclination. These were not vague estimates, they were precise mathematical constraints derived from the immutable ticking of the pulsar's clock. By combining all these independent lines of evidence, scientists could solve the cosmic puzzle with stunning certainty. The numbers that emerged were both elegant and profound. The pulsar itself, the one we could hear, was found to weigh about 1.4 times the mass of our entire Sun. Its silent companion, the neutron star that revealed itself only through gravity, was almost identical at about 1.39 solar masses. Now consider what that means. All that mass, more than our Sun contains, is crushed into a sphere no wider than a modest city, perhaps only 20 kilometers across. This is matter compressed to its absolute limit, where protons and electrons have been forced together to form a sea of neutrons. The density is so extreme that a single sugar cube-sized piece of this material would weigh as much as every human on Earth combined. This precise measurement did more than satisfy curiosity. It provided a critical anchor point for the entire field of neutron star physics. Theorists have long debated the exact nature of matter under such incomprehensible pressure, a concept described by the equation of state of ultra-dense matter. Is it a fluid of pure neutrons, or do stranger particles like hyperions or even free quarks appear in the core? The measured mass of 1.4 solar masses for these objects immediately ruled out many proposed equations of state that were too soft, predicting that neutron stars would collapse into black holes at lower masses. It told us that neutron star material must be incredibly stiff, able to support a staggering amount of weight against its own gravity. The Hulse-Taylor pulsar gave us our first reliable benchmark, a known weight for the densest, most exotic form of matter we can directly observe in the universe. The agreement between prediction and observation is so close it defies everyday intuition. That orbital decay, the slow inward spiral driven by gravitational waves, matched Einstein's theory to within 0.2%. To grasp that level of precision, think of it this way. It is the equivalent of predicting the exact distance from the Earth to the Moon, 250,000 miles, and having your real-world measurement come out within the width of a single human hair of your calculation. That is not merely accurate, it is a staggering testament to the power of nature's own laboratory. Achieving this result was not a matter of pointing a telescope once and writing down a number. It was a monumental feat of sustained, meticulous effort spanning decades. Astronomers had to listen to that cosmic heartbeat day after day, year after year, building up a data set of such exquisite detail that the tiny signal of orbital decay could finally emerge from the noise. But the raw pulses were just the beginning. Before they could trust that the dance was decaying, they had to account for every other possible influence on the rhythm. They factored in the complex motion of the Earth itself, our planet's rotation, its orbit around the Sun, and the Sun's own journey around the center of our galaxy. They even had to consider the subtle drag of the solar system's gravity and the faint, dispersive effect of the thin gas drifting between the stars, the interstellar medium, which could slightly delay the radio signals. Each of these corrections was like clearing static from a faint radio transmission, isolating the pure tone of the relativistic effect. When all that painstaking work was done, the result stood clear and undeniable. This extraordinary precision did more than confirm a theory. It established an entirely new standard in experimental astrophysics. The Hulse-Taylor binary pulsar became the gold standard, the benchmark against which all future tests of strong field gravity would be measured. It proved that the universe itself could provide laboratories of such perfection that they could probe the deepest laws of physics with a clarity no Earth-bound experiment could ever hope to match. The precision of Hulse-Taylor was not the end of the story, but a brilliant beginning. In 2003, astronomers using the Parkes radio telescope in Australia found something even more extraordinary. They discovered a binary system where both neutron stars were active pulsars. This was the double pulsar, officially named J0737-3039. Think of the original Hulse-Taylor system as a brilliant conversation where only one partner speaks. We could hear the ticking of one clock and infer the silent presence of its companion through gravity's pull. The double pulsar, however, is a full dialogue. Both corpses are lighthouses, each beaming its own precise rhythm toward Earth. This changes everything. With two clocks instead of one, scientists gain a stereoscopic view of the entire dance. They can measure the system's geometry with far greater clarity, triangulating positions and motions in a way that was impossible before. The orbit is tighter and faster than Hulse-Taylor's, with the two stars whipping around each other in just 2.4 hours. This frantic pace amplifies all the relativistic effects, making them larger and easier to measure with incredible speed. Most strikingly, because the orbit is decaying so rapidly due to gravitational wave emission, scientists could measure that orbital shrinkage in real time, not over decades. They watched the orbit tighten by about 7 millimeters per day, a direct and visceral confirmation of energy bleeding away into ripples of space-time. This superior laboratory has allowed for tests of mind-bending precision. By tracking the intricate timing delays between the two pulsar signals, astronomers have tested general relativity in this system to within 0.05% accuracy. That is over 4 times more precise than the already stunning Hulse-Taylor results. This phenomenal agreement does more than just reinforce Einstein's theory. It acts as a ruthless filter for alternatives. Any competing theory of gravity must now reproduce not just the classic tests, but also the exquisite dance of the double pulsar. Many proposed alternatives, which seemed plausible on paper, fail this cosmic exam spectacularly. They cannot account for the precise timing of those two clocks without introducing contradictions or unseen forces. The double pulsar has effectively ruled them out, strengthening our confidence that the curvature of space-time is the true language of gravity. Every successful theory eventually faces its most demanding critics. The true strength of general relativity is not that it has never been questioned, but that it has survived every single test we have thrown at it, from the edge of a black hole to the timing of a pulsar's heartbeat. Yet the quest is not over. In fact, the most profound reason to keep testing Einstein's ideas is that we know, on some fundamental level, they cannot be the complete story. Our universe is governed by two magnificent rulebooks: general relativity for the very large and the very massive, and quantum mechanics for the very small. Each is spectacularly successful in its own domain, but they are written in utterly different languages and they fundamentally disagree. Reconciling them into a single theory of quantum gravity is the greatest unsolved problem in physics. This is where binary pulsars transform from confirmers into explorers. They become our most sensitive probes for the cracks where Einstein's smooth, classical geometry might fray into something more granular, where the whispers of quantum gravity might finally be heard. Think of it as stress testing a masterpiece. We are looking for any tiny deviation, any minuscule wobble in the pulsar's orbit that Einstein's equations did not predict. Such a deviation would not be a failure, it would be a discovery, a signpost pointing toward a deeper truth. One of the most promising places to look is in the nature of gravitational waves themselves. Einstein's theory predicts a very specific kind of ripple. It says gravitational radiation should be purely quadrupolar. This means the waves are generated by the changing shape of a mass distribution, like the stretching and squeezing of a dumbbell as it spins. Crucially, general relativity forbids something called dipolar radiation, which would be a simpler back and forth motion, like a single mass bobbing on a spring. Many alternative theories of gravity, particularly those that try to weave in quantum concepts or explain dark energy, predict that this forbidden dipolar radiation should exist. If it does, it would sap energy from the binary pulsar's orbit in a slightly different pattern than pure quadrupolar waves. The result would be an orbital decay that is just a fraction of a percent faster or slower than what general relativity alone predicts. So we listen. We measure the orbital decay of systems like the Hulse-Taylor pulsar and the double pulsar with ever greater precision, hunting for that telltale discrepancy. So far, the silence is deafening. The observed decay matches Einstein's quadrupole formula with astonishing fidelity, tightening the noose around those alternative theories that require strong dipolar radiation. Each precise tick of the pulsar clock is another vote of confidence for the old master, but the search continues because finding even the smallest crack in this magnificent edifice would illuminate the path to a revolution. The ticking of that distant pulsar was a promise written in the language of orbital decay. For 40 years, it told us gravitational waves must be real, that space itself could ripple, but we had never felt those ripples wash over our own world. It was an inference of breathtaking precision, yet still an echo of the real event that changed on September 14, 2015. In the early hours of the morning, a signal swept through our planet. It was not a sound, not a flash of light, but a subtle shudder in the fabric of reality itself. Two enormous black holes, each about 30 times the mass of our Sun, had been circling each other in a final, fatal dance. In their last moments, they spiraled together at nearly half the speed of light and merged into a single, more massive black hole. The collision sent a violent tremor through space-time, a gravitational wave that traveled for 1.3 billion years before it reached Earth. Here, it was waiting for an instrument sensitive enough to listen. That instrument was LIGO, the Laser Interferometer Gravitational Wave Observatory. Think of LIGO as the most precise ruler ever conceived. It consists of two immense L-shaped facilities, one in Louisiana and one in Washington state. Each arm of the L is a vacuum pipe 4 kilometers long. A laser beam is split and sent down both arms, bouncing off mirrors at the ends to recombine. In flat, undisturbed space, the light waves return perfectly aligned and cancel each other out. But when a gravitational wave passes through, it does something extraordinary. It stretches space in one direction and squeezes it in the perpendicular direction. For a fraction of a second, one arm of the LIGO detector gets infinitesimally longer while the other gets infinitesimally shorter. This change is almost unbelievably small, a shift 10,000 times smaller than the diameter of a proton. Yet that microscopic shift alters the path length of the laser light, causing the waves to no longer cancel perfectly. A tiny flicker of light appears in the detector, a whisper from the cosmic storm. The signal from those black holes, named GW150914, matched the precise waveform predicted by Einstein's equations for such a cataclysm. This was the direct detection. The echo had become a shout. The lineage from the pulsar to LIGO is direct and profound. The Hulse-Taylor measurement was the proof of concept that convinced the scientific community to invest decades and over $1 billion into building a machine to catch the waves themselves. It showed that the energy loss was real, which meant the waves were real, and it gave theorists the confidence to predict exactly what the waveform from a merger should look like. When the LIGO team announced their discovery in 2016, the scientific world erupted. The following year, the Nobel Prize in Physics was awarded to three key pioneers of the LIGO project, Rainer Weiss, Barry Barish, and Kip Thorne. In that moment, the two Nobel-winning discoveries were forever linked. The first, in 1993, honored the indirect proof from the silent dance of dead stars. The second, in 2017, celebrated the direct sensation of a space-time quake. One discovery built the road and the other drove down it, opening an entirely new window on the dark, violent universe. That direct detection by LIGO opened a floodgate, but binary pulsars were not finished with their work. They have evolved from proving gravitational waves exist to becoming our most stringent testers of the bedrock principles upon which all physics rests. This cosmic laboratory now probes questions that reach far beyond Einstein into the very constants and symmetries that define our universe. One of the most profound of these is the strong equivalence principle. You may have heard of the simpler version that all objects fall at the same rate in a gravitational field, regardless of their mass or composition. Galileo supposedly tested this by dropping balls from the Leaning Tower of Pisa. But the strong version asks a much deeper question. Does the gravitational energy binding an object together itself fall at the same rate? For most things we can test, the effect is negligible. The gravitational energy holding the Earth together is a tiny fraction of its total mass, but for a neutron star it is a different story. A neutron star's immense self-gravity contributes about 10% of its total mass. If that 10%, that binding energy, did not fall at the same rate as the rest of the star, it would feel a slightly different pull from an external gravitational field. This hypothetical mismatch is called a Nordtvedt effect, named for the physicist who proposed it. In a binary system, it would cause the orbits of two neutron stars with different internal structures to drift in a specific, detectable way. So we watch the dance of pulsars with different masses, searching for any anomalous wobble. The result so far is a resounding silence, a beautiful null result. The orbits show no sign of a Nordtvedt effect. This tells us with extraordinary precision that even the gravitational energy binding a star together obeys the equivalence principle. The universe declares that gravity treats everything the same, down to the energy that warps space itself. It is a foundational symmetry that holds firm under the most extreme stress we can observe. Another constant we take for granted is Newton's big G, the gravitational constant that sets the strength of the attraction between masses. Is it truly constant across the vast expanse of cosmic time, or could it be slowly changing as the universe expands? Some theories attempting to unify gravity with other forces suggest G might vary. Binary pulsars offer a way to check. If G were slowly decreasing over billions of years, the gravitational glue holding the binary orbit together would weaken. The orbit would expand in a specific way over time, an effect separate from the relativistic decay caused by gravitational waves. By meticulously measuring the orbital period of ancient pulsar systems over decades and comparing them to the predictions of general relativity, astronomers can place incredibly tight limits on any change in G. The latest results are astonishing. They show that if G is changing at all, it is doing so at a rate slower than 1 part in 10 billion per year. The gravitational constant we measure in our laboratories today is essentially the same constant that governed the dance of these stars billions of years ago. This stability is a cornerstone for our understanding of cosmic evolution, telling us that the rules of gravity have been unwavering since these stellar corpses first formed. Finally, these systems continue to interrogate the gravitational waves they so famously predicted. Einstein's theory makes a very specific claim: gravitational waves travel at the speed of light precisely. But do they? Some alternative theories predict slight differences, or that the waves could disperse with different frequencies traveling at different speeds. The binary pulsar and its descendants provide a clever test. When a gravitational wave carries energy away, it does not just shrink the orbit, it also changes the orbit's shape in a predictable way. The precise details of how the orbit decays and circularizes over time depend intimately on the speed and nature of the waves causing that decay. By comparing the observed orbital changes against general relativity's detailed predictions, scientists can effectively measure the properties of the waves themselves, even though they are not directly detecting them here. The data once again confirms Einstein's vision. The implied speed of gravitational waves matches the speed of light to within a fraction of a percent. Furthermore, there is no sign of dispersion, meaning high-frequency and low-frequency ripples in space-time travel in lockstep. Every precise tick from these distant clocks tightens the constraints, sculpting our understanding of how gravity communicates across the emptiness. In the quiet, relentless rhythm of a binary pulsar, we find answers to questions about the permanence of constants, the equality of all energy, and the very nature of the ripples in reality. It is a laboratory that keeps asking more of us and in return reveals more of the universe's deepest design. The relentless ticking of a single pulsar gave us a laboratory. Now we are building an observatory from dozens of them scattered across the galaxy. This is the next frontier, pulsar timing arrays. The concept is a stroke of audacious scale. Instead of using one binary pulsar to infer gravitational waves, why not use an entire network of the most stable pulsars we can find, treating the galaxy itself as an instrument? The targets are millisecond pulsars, old neutron stars spun up to incredible rotational speeds by accreting matter from a companion. Their pulses are phenomenally regular, the most perfect natural clocks in the cosmos. By monitoring an array of these celestial metronomes spread across thousands of light years, scientists are attempting something unprecedented: to detect the faint, persistent hum of low-frequency gravitational waves washing over our entire galaxy. These are not the sharp chirps from colliding stellar black holes that LIGO hears. This is a deep, cosmic bass note, a background rumble thought to be generated by the slow, ponderous dance of supermassive black hole binaries. At the heart of most large galaxies, including our own Milky Way, sits a behemoth, a black hole weighing millions or even billions of times our Sun's mass. When galaxies merge, their central black holes are thought to eventually sink to the new core and form a binary pair, circling each other for eons before they finally coalesce. The gravitational waves from these titanic, slow-motion orbits have wavelengths so long they are measured in light years, and their frequencies are so low it might take years or decades for a single wave cycle to pass by. No ground-based detector like LIGO could ever sense them, but a pulsar timing array can. Here is how it works. Imagine the gravitational wave background as a gentle, endless swell in the fabric of space-time. As these waves pass between Earth and a distant pulsar, they minutely alter the distance the radio signals must travel. For a single pulsar, this effect is buried in noise, indistinguishable from other tiny timing glitches. But with an array of pulsars, the signature becomes clear. The wave will affect the timing of pulsars in one part of the sky differently than those in another, creating a correlated pattern across the entire network. It is like trying to sense a gentle, planet-wide ocean swell by watching dozens of buoys scattered across the sea. The rise and fall of any single buoy could be from a local wave, but if all the buoys begin to move in a specific, correlated pattern, you know a vast underlying swell is passing through. Major collaborations like Nanograv in North America, the European Pulsar Timing Array, and others have been collecting data for over 15 years. In recent announcements, they have reported compelling evidence for this gravitational wave background. The data shows exactly the kind of correlated timing deviations across dozens of millisecond pulsars that the models predict. While not yet a definitive detection of a single source, it is a strong signal of a collective hum, a choir of supermassive black hole binaries singing in frequencies far below our hearing. This groundbreaking work stands directly on the shoulders of the binary pulsar timing techniques pioneered by Hulse-Taylor. Their decades of patient observation proved we could use these clocks to measure space-time itself. Now, that same meticulous art of timing has been scaled up into a galactic enterprise. turning the entire Milky Way into a resonant chamber for listening to the deepest voices in the universe. Behind every nanosecond of that cosmic data lies a very human routine. The Pulsar astronomer's day does not begin under a starry sky, but in an office lit by the glow of computer monitors. Their most vital instrument is not a telescope's dish, but a calendar, marked with precious blocks of time allocated on facilities like the Arecibo Observatory in the past, or today on the Green Bank Telescope, the Very Large Array or Parkes. Securing these slots is a competitive science in itself, a proposal written months in advance for a chance to listen to the universe's heartbeat for a few precious hours. When their scheduled window arrives, they might be at the telescope's control room or, more often now, remotely logged in from their university, guiding the massive instrument to point at a specific coordinate in the sky, a point of light that stopped shining millions of years ago. The data that streams in is not a sound or an image, but a river of numbers, a timestamp for every single radio pulse detected, a raw log of cosmic ticks. This is where the real work begins. The astronomer's life is built around code. They write and refine complex software pipelines to clean this data, to subtract the known motions of the Earth, to filter out the static of interstellar space, and to isolate the pure timing signal of the pulsar itself. They are hunting for timing residuals, the minuscule differences between when a pulse was predicted to arrive and when it actually did. These residuals, measured in nanoseconds, are the gold dust. They hold the clues to orbital decay, to Shapiro delays, to the whispers of passing gravitational waves. This requires a particular kind of temperament, one built for extreme patience. An experiment started by a professor might be continued and perfected by their PhD student, and then by that student's student. The data set for the Hulse-Taylor pulsar now spans nearly 50 years, a legacy of careful stewardship passed down like a family heirloom. It is a career that measures progress in millimeters per year of orbital decay, where a single anomalous data point after a decade of observation can spark either a crisis or a breakthrough. The lifestyle is one of meticulous detail and long-term commitment, fueled by late nights, endless coffee, and the quiet, persistent thrill of the hunt. The reward is the moment the numbers finally align, when the graph curves exactly as predicted, and for an instant you are not just analyzing data, you are listening directly to the geometry of the universe, one painstaking pulse at a time. That meticulous work of listening would be impossible without a physical ear turned to the cosmos. The story of pulsar timing is also a story of monumental engineering, of building ever larger and more sensitive ears to catch the universe's faintest whispers. It began with an icon. Nestled in the lush-karst hills of Puerto Rico, the Arecibo Observatory was for decades the largest single-dish radio telescope in the world. Its colossal dish, over 300 meters across, was carved into a natural limestone sinkhole. This giant, stationary bowl could not be steered like a typical telescope. Instead, it listened by moving its receiver platform high above the dish, focusing on different patches of sky as the Earth rotated. It was this immense collecting area, this vast ear, that allowed Russell Hulse and Joseph Taylor to detect the faint, rhythmic signal of their binary pulsar in 1974. Arecibo was the perfect instrument for the discovery, its sheer size providing the sensitivity needed to pick out that metronomic beat from the cosmic static. But the world of radio astronomy did not stand still. New giants arose. In the quiet, radio-protected valleys of West Virginia, the Green Bank Telescope stands as a fully steerable masterpiece. Its dish is 100 meters across, a massive, precision-machined surface that can point anywhere in the sky, tracking objects with exquisite accuracy for hours. On the other side of the world, the Parkes Radio Telescope in Australia, the dish that helped relay the Apollo moonwalks, continued its long legacy of pulsar hunting, its 64-meter dish scanning the southern skies. These instruments became workhorses of precision timing. their improved receivers and pointing stability allowing astronomers to monitor known pulsars with ever greater fidelity. Yet the quest for sensitivity pushed engineers to dream even bigger. That dream is now a reality in the remote mountains of Guizhou, China. Here lies the 500-meter aperture spherical telescope known as FAST. It is the largest single-dish radio telescope ever built, its reflector so vast it could hold 30 football fields. Like Arecibo, it uses a natural depression in the landscape, but its design is far more advanced. Its surface is made of over 4,000 individual aluminum panels that can be adjusted by actuators, creating an active shape that can form a precise parabolic focus on different areas of the sky. A suspended cabin carrying incredibly sensitive receivers is moved by cables and robots to track celestial objects. FAST is not just bigger, it is smarter and more agile. Its unprecedented sensitivity is like turning up the volume on the universe. It can discover pulsars that are 10 times fainter than those found by Arecibo, and it can time the pulses from known pulsars with jaw-dropping precision, reducing the uncertainty in each tick to a fraction of what was possible before. But the revolution is not just in the steel and aluminum of the dishes themselves. The real magic happens in the backroom. In the early days, data came in on reels of magnetic tape, and analysis was a slow, laborious process. Today, the signals captured by these giants are processed by digital backends, ultra-fast specialized computers that can analyze billions of data points per second. They can search for the signature of a pulsar's spin across thousands of frequency channels simultaneously, something that would have taken years of manual calculation. Modern receivers are cryogenically cooled to near absolute zero, drastically reducing their internal noise so that the faint cosmic signal shines through clearly. This combination of colossal collecting area, exquisite receiver technology, and immense computing power has transformed the field. We are no longer just listening to the loudest, closest pulsars. We are conducting a sensitive census of the galaxy's stellar corpses, finding them in ever more exotic binary systems, and using their collective ticks to sense the gravitational wave background. The journey from Arecibo's static dish to fast active eye represents more than just better tools. It is an expansion of our very ability to hear the subtle music of space-time. But raw data is only a collection of numbers. To transform those numbers into understanding, we must build a universe inside a machine. The intricate dance of a binary pulsar, with its warped space-time and radiating gravitational waves, is governed by equations so complex they cannot be solved with pen and paper alone. This is where the silent partner in modern astrophysics takes the stage, the supercomputer. To truly interpret the nanosecond ticks from a pulsar, scientists must simulate the invisible. They construct breathtakingly detailed digital models that replicate the physics of these extreme systems, a field known as computational astrophysics. Imagine feeding the known parameters, the masses, the orbital separation, the spin rates, into a colossal simulation that runs the full machinery of Einstein's field equations. The computer doesn't just calculate an orbit, it calculates the dynamic curvature of space-time itself at every point around the two stars. The output is not just a number for orbital decay, it is a visualization, a movie of reality. You can watch the fabric of the universe flex and breathe as the neutron stars whirl, see the gravitational potential wells deepen and shallow, and witness the actual generation of gravitational waves like ripples spreading from stones tossed into a pond of space-time. These visualizations are more than just pretty pictures, they are vital diagnostic tools. They allow theorists to see if their numerical solutions match the subtle patterns hidden in the pulsar timing data. But the simulation goes deeper into the stars themselves. What is happening inside those ultra-dense spheres? To understand how a pulsar's spin evolves or how its immense magnetic field is generated, scientists run separate, massively parallel simulations of neutron star interiors. They model a sea of neutrons under crushing pressure, simulating exotic states of matter and the dynamics of superconducting fluids that generate magnetic fields billions of times stronger than Earth. Each of these simulations can consume millions of CPU hours on the world's most powerful supercomputers, like those at national labs. The data they produce is astronomical in its own right, often measured in petabytes. This work represents a futuristic career path that barely existed a generation ago. It sits at the thrilling intersection of theoretical physics, advanced software engineering, and big data science. The modern astrophysicist must be a master coder, writing algorithms to solve equations that describe the fundamental nature of reality. They must be a data wrangler, managing and analyzing outputs of unimaginable scale. And they must remain a physicist, asking the deep questions that guide the simulation in the first place. It is a discipline where the tool is a city block-sized cluster of processors, and the product is a window into the heart of a dead star light years away. The story of that distant ticking star has become a bridge from the classroom to the cosmos. In physics departments around the world, the Hulse-Taylor binary pulsar is not just a footnote, it is a cornerstone. It transforms the dense, abstract mathematics of general relativity from a theoretical exercise into a tangible narrative. Students learning about curved space-time for the first time are no longer asked to simply accept Einstein's equations, they are shown the graph. They see the real data points collected over decades, tracing the steady inward spiral of two neutron stars, a line that matches the prediction with breathtaking exactness. This is no longer a thought experiment about elevators in free fall or bending starlight. It is a documented event, a cosmic laboratory report written in the rhythm of radio waves. That connection is powerful. It makes the profound feel possible. For a young mind grappling with complex concepts, seeing a real-world validation of such an elegant theory can be the spark that ignites a lifelong passion. The system features prominently in standard textbooks, not as an advanced topic, but as the quintessential example of strong field gravity in action. Its elegance lies in its simplicity, a two-body problem where the deviations from Newton are huge, measurable, and beautifully explained by one coherent framework. This clarity makes it a favorite subject for professors who want to demonstrate how science actually works, how patience, precision, and a willingness to listen to the universe can converge into a Nobel Prize-winning understanding of reality itself. Beyond the lecture hall, the story reaches even wider audiences. Planetarium domes across the globe come alive with shows that animate this celestial dance. Narrators guide viewers through the discovery, using stunning visualizations to illustrate the warped space-time and the emission of gravitational waves. Documentaries weave together archival footage of Arecibo, interviews with the scientists, and supercomputer simulations that make the invisible forces visceral. Online, interactive simulations allow anyone to play with the parameters of a binary system, adjusting masses and distances to see how the orbit decays, bringing the physics directly to your fingertips. These resources demystify the science, stripping away the intimidation factor and replacing it with wonder. They show that the most profound discoveries are not made in sterile isolation, but through a very human story of curiosity, collaboration, and decades of dedicated work. For a high school student watching a documentary or a college freshman tinkering with an online simulation, the message is clear: the universe is conducting experiments and we have the tools to understand them. This can be a powerful motivator, steering young people toward degrees in physics, astronomy, computer science, and engineering. They see a path where their skills in coding, data analysis, or instrument design could contribute to the next great discovery, whether it is finding a new pulsar, improving a telescope's sensitivity, or analyzing the data from a gravitational wave detector. The legacy of Hulse and Taylor, therefore, is measured not just in arcseconds of periastron advance, but in the countless students who have looked at a graph of orbital decay and felt a sense of awe. It demonstrates that groundbreaking science is often a marathon, not a sprint, a lesson in the value of long-term commitment in an age of instant results. It proves that even the most esoteric theory, when connected to a tangible, ticking reality, can capture the imagination and inspire a new generation to look up, to listen, and to ask the next great question of the cosmos. The precise rhythm of a dead star echoes far beyond the pages of scientific journals. It resonates in our art, our stories, and our shared dreams of the future, becoming a symbol woven into the fabric of modern culture. Perhaps the most iconic example is a simple, haunting image. In 1979, the English rock band Joy Division released their debut album, Unknown Pleasures. Its cover, designed by artist Peter Saville, featured a stark, white-on-black series of stacked, wavy lines. This was not abstract art. It was a direct reproduction of the radio signal from the first pulsar ever discovered, CP 1919-1, as published in the Cambridge Encyclopedia of Astronomy. The image captured the public imagination, transforming a scientific data plot into a symbol of isolation, mystery, and relentless mechanical rhythm. It spoke to a generation, proving that the cold data of the cosmos could carry profound emotional weight. That same ticking has set the stage in cinema. In the film Contact, based on Carl Sagan's novel, the first signal from an extraterrestrial intelligence is not a spoken message, but a series of prime number pulses, a concept directly inspired by the metronomic perfection of real pulsars. The movie portrays scientists using the Arecibo telescope, the very instrument that found the Hulse-Taylor binary, listening for order in the cosmic noise. This artistic choice rooted a science fiction story in real scientific hope, suggesting that if we are to find company in the universe, it might announce itself with a rhythm as reliable as these celestial clocks. Beyond album covers and movie plots, pulsars have fired our most ambitious navigational dreams. Science fiction authors and scientists at NASA alike have proposed a visionary idea, using pulsars as a galactic positioning system. Imagine a future spacecraft traveling in the profound darkness between stars. Traditional star charts would be useless as the familiar constellations warp and shift. But a pulsar's beacon is identifiable by its unique spin frequency, its cosmic fingerprint. By locking onto the signals from 3 or 4 known millisecond pulsars, a ship's computer could triangulate its position anywhere in the galaxy with astonishing accuracy. These spinning corpses would become lighthouses for interstellar voyages, their immutable rhythms providing a fixed grid for the cosmos. This poetic concept transforms them from distant curiosities into practical tools for a spacefaring civilization, a bridge from our current understanding to an imagined future. At its heart, this cultural fascination taps into something deeply human, our longing for order and our awe of time. For millennia, we have looked to the heavens to mark the seasons, to build calendars, to find a rhythm larger than ourselves. The binary pulsar is the ultimate expression of this quest, a natural clock of unimaginable precision ticking in the void. It represents a universe that is not chaotic, but governed by elegant, discoverable laws. It bridges the cold, hard truths of general relativity with the warm, boundless reach of human imagination. We see in its steady decay not just a confirmation of physics, but a narrative, a story of a slow, inevitable dance toward an unseen end. This duality is its lasting power. It is both a precise instrument for testing reality and a profound symbol that inspires us to dream of navigating the stars. That steady rhythm from deep space faces a new kind of interference, one born not from cosmic chaos, but from human ambition. Our ability to hear the universe's faintest whispers depends on a fragile silence, a quiet increasingly shattered by our own technology. Radio astronomy requires radio quiet zones, protected slices of the electromagnetic spectrum where we can listen without the constant buzz of modern life. These zones are like nature reserves for discovery. places where the faint tick of a pulsar billions of light years away isn't drowned out by a passing cell phone tower or a television broadcast. But the greatest threat now comes from above, from a glittering new constellation in the night sky. Companies are launching tens of thousands of communication satellites, forming mega constellations like Starlink to provide global broadband internet. While the goal of connecting the world is a powerful one, these satellites come with an unintended cost. Each one transmits radio signals, and in aggregate, they create a pervasive electronic haze across the very frequencies astronomers use to listen to pulsars and peer into the early universe. Imagine trying to hear a single, delicate violin note from across a crowded stadium where everyone is shouting. That is the challenge now facing our most sensitive telescopes. The faint, precious pulses that have guided our understanding of gravity for decades are at risk of being lost in a sea of digital noise. This creates a profound ethical and practical dilemma for our technological age. On one side lies a powerful humanitarian and commercial imperative, bridging the digital divide and bringing high-speed internet to remote and underserved communities across the globe. The promise is one of universal education, economic opportunity, and connection. On the other side lies a different, more silent form of human progress, our fundamental quest to understand the cosmos and our place within it. This is not merely about preserving a niche scientific hobby, it is about safeguarding a vital window into physical reality. The data from pulsars and other radio sources informs our understanding of fundamental physics, tests the laws of nature, and even aids in practical endeavors like deep space navigation. If we lose the ability to conduct this pure, curiosity-driven science, we lose a unique pathway to knowledge that has no commercial substitute. The question becomes stark: who owns the sky? Do we prioritize immediate terrestrial utility, or do we preserve a channel for long-term cosmic discovery? This is not a simple choice between good and bad, but a complex balancing act between two competing visions of a technological future. The resolution will not come from a single country or company, but through international regulation and cooperation. Bodies like the International Telecommunication Union help allocate radio spectrum, acting as global referees between competing needs. Astronomers are now engaged in urgent negotiations with satellite operators, working to design satellites that are radio dark in the protected bands and to develop advanced software that can algorithmically remove satellite interference from their data. It is a race between technological problem solving and the accelerating pace of launches. The lifestyle implication here is subtle but significant. Our collective choices about connectivity are shaping what we can and cannot learn about the universe. The silent laboratory built by colliding stars endures, but our ability to listen to it hinges on decisions made in boardrooms and regulatory meetings today. Preserving a quiet corner of the radio sky is an investment in wonder, a guarantee that future generations will still be able to hear the cosmos ticking and continue the conversation that began with a single metronomic beep. The clockwork of their dance is slowly winding down. For billions of years, the Hulse-Taylor pulsar and its silent companion have been locked in a slow, relentless spiral, their orbit decaying by a few meters each year as gravitational waves carry their energy away into the void. This is not a story with an indefinite future. It has a final, spectacular page. Project the mathematics forward and you see the inevitable conclusion. The two neutron stars will continue to draw closer together, their orbit tightening, their dance accelerating from a frantic 8-hour loop to a matter of minutes, then seconds. In the final moments, they will whip around each other at a significant fraction of the speed of light, distorting the space between them into a violent whirlpool. Then they will collide. This ultimate merger will be a cataclysm of almost unimaginable power, a flash of energy that outshines entire galaxies for a brief instant. The final burst of gravitational waves from that collision will be a loud, clear shout in the fabric of space-time, a signal that carries the signature of their masses, their spins, and the very nature of the exotic matter they are made of. And when the storm of energy subsides, the most likely result is a new, silent monument, a black hole containing the combined mass of two dead stars. This is the cosmic story that our patient observations have allowed us to read, a narrative with a beginning, a middle, and an end, all written in the language of orbital decay. We have witnessed the middle chapters, the steady, measured spiral, and through LIGO, we have now seen the final page of other, similar stories, the brilliant flash of waves from black hole and neutron star mergers in distant galaxies. The Hulse-Taylor system provides the prologue and the detailed plot for those explosive finales. It is a profound thought that scientists on a pale blue dot, listening to the faint ticks of a dead star, have not only decoded the laws of gravity, but have also foretold the spectacular fate of a system that will not meet its end for eons to come. The universe's most profound truths are often written in its quietest rhythms. For nearly 50 years, the steady beep of the Hulse-Taylor binary pulsar has been a teacher, a referee, and a prophet. It began as a cosmic oddity, a ticking star with a strange, rhythmic hitch in its signal. It became the ultimate natural laboratory, a place where Einstein's most daring predictions about warped space-time and rippling gravity were tested not in thought experiments, but in the hard, precise data of orbital decay and shifting clocks. Its legacy is a cascade of confirmations, the periastron advance of its ellipse, the slowing of time in its gravity well, the Shapiro delay of its light, and most famously, the slow, unwavering inward spiral that proved gravitational waves were real long before we felt them wash over our own world. This single system bridged the gap between mathematical elegance and observable reality, earning one Nobel Prize for its discovery and paving the intellectual road for another, awarded for the direct detection of the waves it first implied. But its work is far from finished. Today, this legacy of precision lives on in the hunt for quantum gravity, in the constraints on nature's fundamental constants, and in the vast, silent listening of pulsar timing arrays that sense the hum of supermassive black holes. The takeaway is timeless and deeply human. By patiently, meticulously observing a subtle tick in the darkness, by dedicating careers to listening, we can unravel the deepest laws governing all of reality. We learned that gravity is the geometry of a dynamic universe, that time is malleable, and that space itself can ripple. All of this was decoded from the rhythm of a dead star's final spin. So the next time you look up at a quiet, star-filled sky, remember the music hidden in the silence. Those points of light are not just decorations. They are experiments in progress, clocks ticking down to cosmic collisions, laboratories testing the fabric of existence. Stay curious. Support the fundamental, curiosity-driven science that asks big questions with no immediate application. For it is in that pure pursuit of understanding that we find our place in the cosmos. You never know where the next universe-shattering clue might be hiding, in the next faint rhythm, the next anomaly in the data, the next patient observation that begins with a simple, persistent question.